All right, this is going to be a combination to Lecture 12, which I did last Monday before the exam, just a short introduction to reflection and refraction. And then I'm going to talk a little bit about total internal reflection and dispersion. Most of Monday's in-class time will be actually learning how to use Snell's law and how that applies to total internal reflection and what dispersion is. All right, so we talked a little bit about what reflection and refraction are. Reflection is when something bounces off of a surface, and refraction is when it passes through the material. All right, so you can also be absorbed, but we don't really care quite as much about that unless you're worrying about how something heats up. All right, so we get to the easiest equation in physics, the law of reflection. Light comes in at some angle. From the normal, the perpendicular, to wherever on that surface it hits, it bounces out at the exact same angle. So we're going to be using that a lot for the next lecture, Lecture 14, when we're looking at curved mirrors and how those affect how an image is formed. But basically what happens is when light goes into a material, it slows down compared to a vacuum. And basically what happens is the index of refraction tells you how much it slows down. And so in the material, we have the speed of light v. In a vacuum, it's the speed of light c, which is 3 times 10 to the 8th meters per second. And then the index of refraction is just a dimensionless constant for any material. Though constant we use a little bit loosely at this point, as you'll see by the end of this video. All right, the speed changes, but the frequency remains the same because the light comes in. It's basically, think of light as just a series of pulses of electric and magnetic field, and you'll get a maximum, and the frequency is just how many times per second those maximums hit the barrier. So they come out the same number of times per second, but as the light travels through the material, it either is going faster or slower. So the frequency stays the same, the wavelength has to change. So it turns out the wavelength gets shorter, shorter as it goes into a material, depending on how much it slows down. I always mess myself up on that one. I don't know what's going on there. The frequency stays the same. Just worry about this last result. Lambda 0 is the wavelength in a vacuum, which you use by finding the speed of light and the frequency. And then the wavelength in the material depends on the speed of light in the wavelength of light in a vacuum and the index of refraction. All right. Then we talked a little bit about Snell's law. It goes from an angle theta 1 to an angle theta 2. We'll do a lot more with this on Monday. And we'll figure out exactly the relationship between those two is what's called Snell's law. The index of refraction of the first material times the sine of the angle that it enters relative to normal. If you use relative to the boundary, you use cosine. That's the only difference. Is equal to the second material times the sine of its angle. So basically what happens if you're going from a low index of refraction to a large index of refraction, the angle gets smaller. It bends toward the normal, back and forth. All right, so one consequence of this is, if you've ever been at the bottom of a pool or something like that, if you look up, you can only see out in a certain region, right? If you look further and further away, you just can't see out of the pool because the light, as it's going along, is reflecting. The surface is acting like a mirror, which is kind of strange because light travels between water and air very easily once you get to certain angles. Because what's happening, as you increase the angle going from water to air, so in water, the index of refraction is larger, it's about 1.33, and the index of refraction of air is smaller, it's about 1, you get a larger angle. So as you increase this angle, eventually you get to a point where the angle of refraction is 90 degrees. So if you bend light to 90 degrees, none of it escapes. And then if you go above this critical angle, so the dashed line here represents what's called the critical angle, you get what's called total internal reflection. So the light, instead of escaping, all of it bounces in. The surface of the water acts like a perfect mirror. All right, so for total internal reflection to work, we have to have N1 greater than N2. It doesn't work otherwise. And we're going to call, at our critical angle, we're going to call theta 1, our critical angle, theta 2 is 90. So that's that case with the dotted black line from before. Light comes in at a specific angle and it refracts to 90 degrees. So we just use Snell's law, but we're going to get a slightly different version. I'm going to plug in different values here. N1 sine of the critical angle is equal to N2 sine of 90. Sine of 90 is 1, so we get that N1 sine of the critical angle is equal to N2. So my critical angle is N2 over N1, or this inverse sine of that. So this is the condition for the critical angle for total internal reflection. Any angle greater than this for this specific boundary between N2 and N1 will give you reflection and not refraction. So we'll look at how the effects of that on Monday. Kind of looks at it if we're going from glass to air. It can go straight through, can bend. The little dashed line here is the critical angle. Anything above that critical angle, you get reflection. All right, the last kind of application that we're going to have for right now of refraction is what's called dispersion. So those of you who are big fans of Pink Floyd and the Dark Side of the Moon, you recognize images like this. This is an image I took a long time ago to demonstrate things for a class I was teaching at UCLA, because I could never get prisms to work very well in lecture. We had a nice collimated light beam in lab, and it's just a very small thing. It was hard for a lot of people to see, but I just took a picture of it. It's on a light table in my old lab. Beam of light coming in, hitting a highly dispersive, so dispersive meaning all the different colors are dispersed, material, and you form a rainbow. Turns out white light is just made up of all these other colors of light. The whole Roy G. Biv, even though indigo is just a made-up color at the time by Newton because he wanted 7 colors. He didn't like the idea of 6 colors. He wanted things to be prime numbers, which, you know, as a math people, they always like such things. But basically, what happens is because the index of refraction changes for different materials, different colors of light that are coming in at the same angle will refract at a different angle. And what happens in general, not always, but in general, the index of refraction is going to get bigger with the higher frequency. So red, which has the lower frequency, to blue, which has the higher frequency, will get different. You'll go from less refraction to more refraction. So blue usually gets refracted more than red. There's just a typical thing for 3 kinds of glass. Starts out at 1.6 for red light, then all the way through blue light kind of drops down. Oh no, sorry, blue light through red light. Mixing things up in my head with wavelength and frequency. All right, so this is just kind of a reference. We'll go over all this stuff in class. All right, thanks.